You probably think of Wi-Fi as just a way to get online, right? But what if those same signals could do a lot more? Today, we're going to talk about a new technology called Doppler Radiance Fields. It comes out of the University of Toronto's Wireless and Internet Research Laboratory, and it's all about teaching Wi-Fi to understand human movement without using any cameras. So here's how we're going to break this down. First, we'll look at the potential of Wi-Fi sensing. Then, we'll get into the big problem that researchers needed to solve. And after that, we'll walk through the breakthroughs, from a method called MORIC to DoRF, and finally, guided DoRF, to see how they built this really robust system.
Let's start with the big picture. What really becomes possible when the Wi-Fi signals that are already all around us can also be used as sensors?
Well, the applications are pretty interesting. In healthcare, for example, you could monitor someone's sleep quality without them having to wear any device. For smart homes, lights could turn on or adjust just based on you walking into a room. And for things like virtual reality and gaming, this can make experiences a whole lot more immersive, all by using the Wi-Fi that's already there.
But for a long time, there was this one major hurdle that kept this kind of technology from really working outside of a lab.
And that issue was something called poor generalization. Basically, a system would work fine if you trained it on one person in one specific room. But as soon as you brought in a new person or even just moved a chair, the accuracy would drop. It just wasn't reliable enough for the real world.
So, the first real breakthrough came when researchers started looking at the physics of the problem, focusing on the direct effect that motion has on a Wi-Fi signal. To understand this, we need to talk about the Doppler effect. You know how when an ambulance is coming toward you, the siren sounds high-pitched, and as it passes, the pitch drops? That change in frequency is the Doppler effect. It turns out your movement changes Wi-Fi waves in the very same way. And here's the key idea. A Wi-Fi signal doesn't just travel in a straight line. It bounces off walls, furniture, and people, creating dozens of different paths. The new perspective was to treat each one of these paths like its own tiny one-dimensional camera, with each one capturing a little slice of the motion from a totally random angle. This led to the first method, called MORIC. That's M-O-R-I-C. The whole point of MORIC was to take all of those scattered one-dimensional views and figure out how to piece them together to identify an activity, even though no single view had the full picture. And it worked. For a pretty tricky task, telling the difference between 4 distinct hand gestures, MORIC got an accuracy of 56.3% on people the system had never seen before. Now that's a big jump up from 25%, which is what you'd get by just guessing. It showed they were on the right track. Okay, so that was the first step, but you still only have these scattered, incomplete views. The next logical question was, what if you could put them all together to create a complete picture? And that's where DoRF comes in. It's spelled D-O-R-F for Doppler Radiance Fields. What DoRF does is it takes all those random 1D camera views and uses them to reconstruct a full 3D model of the motion. By creating this more complete model of the motion, DoRF was able to increase that generalization accuracy even more, up to 58.9%. It was another clear improvement, showing that having that 3D representation really helps the system understand movement better.
But, even a great 3D model is only as good as the data it's built from. So the final piece of the puzzle was cleaning up the input signals.
The team found that some of those Wi-Fi signal paths were just noisy. They were producing bad data, and these bad data points, or outliers, were throwing off the 3D model and making it less accurate. So the solution was to create a guided version. Guided DoRF is smart enough to look at all the incoming signals first, find the paths that are noisy, and just get rid of them before it even starts to build the 3D model. And this refinement, just cleaning the data first, led to another pretty big jump in performance. The final accuracy for that same 4-class hand gesture test went up to 65.3%. It's also worth pointing out, if you give this system an easier task, it does even better. For a simple binary choice, like telling an up-down gesture from a left-right gesture, the accuracy can get as high as 90%. So let's put all of these improvements together and just look at the full journey, from a system that was essentially guessing to one that actually works reliably. This chart really tells the whole story. You start with the raw Wi-Fi signals, where performance is stuck at chance, just 25%. Then MORIC's insight about 1D cameras jumps it up to over 56%. Building the full 3D model with DoRF gets it to almost 59%. And finally, guiding the system by removing noise takes it all the way to 65.3%. You can really see this step-by-step progress.
So what this work really does is provide a powerful new tool for sensing human activity without needing cameras or wearables. It kind of leaves us with a pretty interesting question. Now that we can teach our Wi-Fi to see movement, what are we going to teach it to see next?